Going to take a look at inference. What is statistical inference? Well, we collect data, but why do we do it? We collect it for a purpose so we can use it. And then from the data we collect, we can infer things. It does make some assumptions though. It assumes that the sample data that we've collected actually is valid to be used to make predictions. But what is it? It's when we select from, it could be a finite population or an infinite number. It doesn't matter. We're just selecting a group of objects. Why do it? Well, it's going to be quicker than gathering every piece of possible information. It's certainly going to be cheaper. Like if you're going to survey people, you've got to pay someone to do that. So if I went and surveyed every single possible person, that's going to cost me a lot more. Accuracy, this is the interesting one. The more data you collect, the more chance there is of making a mistake. And so when you collect really large samples, the data actually tends to be less accurate than when you grab a small sample. And this one, necessity. The example I've got there is, imagine if you wanted to quality test matches that you were making, and you went and tested every single match. Yep, that one worked, that one worked, that one worked. Well, then the matches are useless. I mean, it's just not practical to do that. So for that reason, no, you would only test a sample to see how the matches are going. How should you pick your samples? And it should always be randomly, right? Because you don't want any bias at all. So you just randomly select from the population that you're choosing from. That way, there's, as I say, there should be no bias and no predictability amongst. However, the thing with random samples though, what you can't guarantee is that it will be the same as the population. In other words, the cross-section might be different. For example, say I was going to sample people from this class. Now there's a certain ratio of, say, males and females. But if I was to only sample, say, from these two tables, well then the ratio of males and females is not the same. So generally your sample is going to be very hard to have the same overall characteristics as the group you're selecting from. All right. Terminology then. There's subtle differences from when we're looking at all the data or when we're just looking at a sample. So when we're collecting it, survey is when you're just sampling. If you were to get every piece of information, that's when we call it a census rather than a survey. The way we write it down, probability when we're talking about a population, relative frequency when we're talking about the sample. Expected value, yes, they are both saying mean or average, but the symbols we use. We tend to go with the Greek letters when we're talking about the population, whereas the Roman or the Latin letters when we're talking about a sample. So for expected value we use mu when we're talking about population, but x with a bar over the top when we're talking about a sample. And for variance, we use sigma squared for population, but s squared for sample. And what should happen is, as that sample size gets bigger and bigger and bigger, approaches infinity if you like, then those values from the sample to the population should get closer and closer to being the same. Well, clearly, if you've got an infinite population and you sampled an infinite, well, really you've sampled everything, so it would be exactly the same. Let's have a look at this. Then roll 2 dice. First thing I'm going to do is the theoretical probability. So what would actually happen? So I've drawn it up there in a table, and I used a spreadsheet to do all the hard work for me to work out what the probability was, and then the xpx and the x squared px. So from that I can see that the expected value is 7. The variance turns out to be 5.83, or 3 repeater. So there's my deviation, 2.4152. I've done it in 4 decimal places. And that would be the graph of it. It's a lovely symmetric graph. But now we're going to do it 50 times, then 100 times, then 500 times, and then 1,000 times, just to see how it compares. And of course, I got a spreadsheet to do the work for me. Up the top, I've got the theoretical probability. Down the bottom, the experiment. So first of all, I've got the spreadsheet to roll it 50 times, and this is what it came up with. The expected value was 6.42. So it's out by 0.58 from the theoretical. The variance, 5.8036, which means the difference in the deviations ended up being 0.00 0.61. I've layered on top of that graph of where the relative frequency is to see how close it fits the data, and it's okay in bits, but you can see up the top here it's way off and what have you. Alright, well what we're saying is as we roll it more and more times, we should get closer and closer to that picture. So 100 times, and this is what my spreadsheet came up with, expected value of 7.16, out by 0.16, and my deviation was out by 0.025. There's the graph. It's getting a little bit better. So then I did it 500 times, and my average or expected value was out by 0.14. My deviation was out by 0.04, you may as well say. And we can see, yeah, it is starting to come towards the theoretical. So the last one, when I did it 1,000 times, the expected value ended up being out by 0.042 and the spread 0.06. When I layer that on top, actually now it's getting really close. Now, I didn't just make those up. That genuinely was just randomly getting the spreadsheet to do it, and that's what it came out as. Of course, there's no reason why it had to come out like that. I mean, because it's random. It could have been completely off. Maybe I just got lucky. But you can see, the more times I did it, the more chance I've got of getting closer and closer to the actual data itself. 13D, it's a little bit different, that exercise. I've only picked 4 out there for you to have a go at.